Okay, so this week we'll cover linear regression, logistic regression, and decision tree. Uh, that's the goal. Let's see how far we're going. So, starting with like a very broad overview of different machine learning tasks. So, if we categorize different machine learning tasks into like a few broad categories, they will be coming under supervised algorithms, unsupervised algorithms, semi-supervised reinforcement algorithms. And apart from them, there are few more algorithms also. They are called self-supervised, active learning, curriculum learning, lifelong learning. So, but they are like kind of bit of advanced things, so we're not discussing about them. So majorly as part of your syllabus, so we'll be discussing supervised and unsupervised quite a bit. And if time permits, one class on reinforcement. Right. Supervised, already you have seen few algorithms like we have discussed SVM. Also, Sarah discussed like neural networks. So they are all under supervised algorithms. Also, like these are like kind of very broad. So if you again categorize these algorithms onto like some subcategories, so supervised can be broken down into like kind of classification and regression. So we'll see what are these classification and regression scenarios. Let's first understand what these four paradigms are. Supervised, like it requires like training, like the training data requires like requires X and Y pairs, like input features and the corresponding Y labels. It can be classification and regression. So given XY pairs, you will train a model. Then once the model is trained, given a new data, you will predict the Y. Unsupervised, you don't have the Y labels. You have only input data X, and you kind of try to learn the representation of the input data, how the data are kind of segregated into different representations that you want to, different representations or groupings that you want to learn in the unsupervised. We'll discuss KNN and K-means under unsupervised. Um, yeah, now coming to semi-supervised. Semi-supervised initially starts with some level data where X and Y, like Y levels are given for some X data points. Then it continue with the on-level data. Like we don't have a bunch of like abundant amount of level data there. We just like initialize the algorithm with some level data. Then we leverage like abundantly available on-level data. In reinforcement, you have like kind of like agent that is playing with environment, like it is like asking something to environment, getting some feedback from the environment. So that's kind of a reward feedback or punishment feedback. Then it is learning on its own. Now coming to two major subcategories of this kind of supervised or unsupervised algorithms. They are called classification and regression. So when we say something as classification task, when we say something as a regression task, if the Y level corresponding to X, the data X is like kind of discrete, then it is called classification task. If it is continuous, then it is regression task. Some classic examples for classification are image recognition, text classification. For regression, it is stock market prediction, weather forecasting. You can think of many more examples. Right. So let's get started into linear regression. Yeah. So if you break down linear regression into two words, one is first component is linear and the second component is regression. We understood what regression is. Now, why this linear part is there? So what linear component tells us, like we have this X as like another input feature and input data you can say, and Y is like kind of the independent variable. So whatever the input data given to us, X can be like a one-dimensional data or multi-dimensional data, that they are called the dependent variables. Sorry, they are called the independent variables, and Y is called the dependent variable. Like Y is depending on the X. So X doesn't depend on anything. So X is independent variable, right? So given dependent variable Y, independent variable X, linear regression assumes there is a linear relationship between these two X and Y. So this F represents the model here, and theta is the model parameter, and this F will be linear model. So this we know from our like elementary mathematics. Again, we discussed in the SVM class also. Like we know this Y equal to mx plus c. But there is something extra to it. Like it's not only Y equal to mx plus c. There is a parameter called kind of epsilon. That's the error. So what is this error? This is not the prediction error. This is the measurement error. When we measure something, let's say we're kind of trying to compute the velocity given distance and time. Like you are doing some mechanical calculation, right? So those measurements error are kind of assumed to be captured through this epsilon. And during like ML algorithm setup, we generally consider this epsilon as the normal distribution, like kind of random noise with normal distribution mean zero, and some significant and very small standard deviation. Okay, so here y is the ground truth and y dash is the predicted output. So these are the two major things you need to know. Another very important thing is so what is this m? So m is the slope. Like whatever this line is like this is one D feature, so you can easily visualize. So x and y, so there is a slope here. If you kind of try to fit this line for this given regression data, so whatever the slope you're getting, so let's say this is the slope, right? So this is the slope, right? So what this slope tells, like the change in y for one unit change in x. So this is very important concept. So you might feel very lame concept, but this is very important concept. So I'm like giving one like kind of pre-hint about your quiz or and some question. So one particular question will come based on this concept only. So the change in y for unit change in x, right? So it's not like if x is not changing, we cannot compute the change in y, right? So that's what the major concept behind linear regression. If x is static, we cannot apply linear regression. Why you cannot apply linear regression? We'll see that, right? So this is one example scenario. So you have x and y, and you are fitting a regression line, and somehow it is looking nice. But there are scenarios where it may not look nice. So towards the end of the class, we'll see about this. So when the input feature is one dimensional, this is particularly called the simple linear regression. And when the input feature is multi-dimensional, it is called multiple linear regression, right? So like how it is different in simple linear regression, if you see only like instead of m like going ahead, I will be writing wi only. So only one w is involved, and obviously the bias parameter is there. But in multiple linear regression, corresponding to every dimension, we have a particular w, right? So if we have p dimensions, we have p w's, and of course one b parameter is there. So number of parameters in multiple linear regression, if there are p dimensional input, it is p plus one, right? Now again going about the like kind of broader setup, and how do we compute the error? So what is the error in term, like when we have a ground truth y and predicted y hat, we should have some kind of measurement to say, okay, whether y hat is close to y or not, how close to y, right? So, so what is the setup? Given input data is xi, yi. So n number of input data points. So this is not capital N. So this is small n. Yeah. So what is your model? It's a linear model, W transpose x plus b. So again, this W can be d-dimensional depending on the dimensions of the each x input, right? So what is the important component for this slide is what is the loss. So loss here is the squared error loss. So this you have already seen like in part of like neural network loss, like sigmoid loss and squared error loss. But particularly for linear regression, only we will throughout discuss only the squared error loss. So here I am saying this is the sum square error. So you can convert this into mean square error by like kind of just multiplying 1 by n, right? So this is not very significant. Like all the formulation I will be showing you is using sum square error, but you can just multiply 1 by n and nothing will change, right? So that will so if you multiply this will convert into MSE, mean square error. Okay, so what is this error? The like for every input data point, difference between yi and yi hat and the square value of it, right? Then so yi hat you parameterize through b and w. So this is b plus w wxi, right? So what is the goal of our like learning algorithm? We want to find those optimal w and b that minimizes this function. This is the loss function, right? So that's why you have written R min. Our target is to find W and B that minimizes this function. right? So if we again another representation modification going ahead, I will not be writing b plus w xi explicitly. So b we can write directly part of this w vector, and corresponding x will be 1. Right? All these things you should be knowing. Right. So there are few assumptions in the linear regression, and again, this all these 5 points we'll discuss again towards the end of this class. These are assumptions, and these are the limitations also. So first assumption is it assumes linearity between x and y. Second assumption is independence. The n observations we have, right? So all the observations it assumes to be independent of each other. This is something new terminology you have not heard of, homodiscosity. So what it says, the error variance is constant across all levels of predictor. What is the error variance? So this is the error. So what error we are talking about? This mechanical error we are talking about. So this particular error has a variance sigma square, right? So that's what it is saying. Error variance is constant across all levels of predictor. So if you have x1, you have x2, you have xp, whatever the predictors you have, for every predictor, the error variance is same. Then normality, again, the errors are normally distributed. That's the assumption. So there are like fancy algorithms where the error is not normally distributed. How do you do that? So, but as part of your syllabus, it's not covered. Right? Another very important point, multi-collinearity. Linear regression assumes the features are like kind of not very strongly correlated. Features meaning, so these are the features x1, x2, xp. They are the features. They are not very strongly correlated. So they can be correlated, but the correlation amount can be very small. If they are very strongly correlated, so there will be some issue. So we'll discuss what will be the issue and how we'll address that. Right. So this is the complete setup and the loss function. Now we'll see how do we compute this W and B. We know these are the like kind of the parameters we want to learn. So once we know these parameters, given a test data point, we can directly multiply W transpose X plus B, W transpose X test plus B. So now our complete goal will focus on how do we compute this W and B given data point. Right. So we'll follow two approaches. One using calculus. But it will be little bit rigorous. We'll discuss for one-dimensional case and multi-dimensional case, and another using just simple linear algebra. Okay, let's start with how do we approach using calculus. So again, this is very intuitive. You know how do we do this? So we are given the loss function, and there are only two parameters. We'll kind of do the partial derivation with respect to each parameter for B, then for W. So if you like, these are simple mathematics. If you do this, you will get this equation for B. For W, you will get this equation. Now you simplify. How do you simplify this? First, try to eliminate like B from this equation. If you once you eliminate B and represent in terms of W here, then put the value of B here, and you will try once you solve both of these two things, you will get W and B equal to this. This is for the one-dimensional case. Again, you can try to solve this at your home. I'm not solving it in detail because there are much more important formulations to be solved. Right? So this is very simple. You can just solve for B here from this equation, put the value of B in this equation, I will get this W and B. Okay, so this is also one more potential area where you might expect one question. I don't know whether quiz or answer. Okay, because I have left out the thorough derivation, so there are some tricky part in the thorough derivation. So you might expect some question there. Yeah, so now coming to multivariate least square regression. So why I said least square suddenly from the linear regression. So this squared error is because we are trying to minimize this. The other name is least square regression also for the linear regression, right? So linear regression, other name is least square regression. And many times, if you see like kind of the textbooks, they will append one prefix also, ordinary least square regression. What is ordinary about this ordinary least square regression? We will discuss towards end. Okay. So whatever we'll be discussing throughout your syllabus is ordinary least square regression, but what are the other variants we'll discuss first. Okay, now coming to multivariate least square using calculus. Again, this is multivariate least square, but this is again ordinary. Why it is ordinary, we'll discuss in the end. So in the multivariate case, we know we have x has multiple dimensions. So we can like kind of represent this as xw. So if x is, let's say, n cross p, and w is p cross 1. This will be xw will be n cross 1, and y we know n cross 1, right? So dimensions match correctly. Right, we can like kind of crisply write this formulation using this formulation. Right now, what we have to do, we have to again because we are saying we will do through compute W and B using calculus. So we have to kind of do the partial derivative. So before doing partial derivative, let's simplify. So what is this? This is the square of the second norm. So what is second norm? Second norm, let's say there is a vector V. What is the second norm? Second norm is summation of I Vi square, whole root of this is the second norm, right? So I'm saying this is the second norm square. So square root over like the root over will go away. So the LW is say square of the second norm. So how can I represent the square of the second norm? So this is just y minus xw is a vector, right? So because we are squaring this, we can easily write this using transpose. Okay, this is a simple matrix algebra or vector algebra. So you might have learned in as part of your linear algebra. So I'm not going over them. Now you will kind of like open this multiplication: y transpose y, x w transpose y transpose x w, all these things. Now if you simplify, so you'll get this LW is this term. Now we have to compute the partial derivative on this term only to get optimal W and B. So first, doing the partial derivative with respect to W. So again, so these are there are some notions of vector algebra is being used here, like matrix derivative or directional derivative, you can say. So if we are given delta of A transpose X with respect to del X, it will be A. So A is a vector. So this is what we are doing here. So if you try to kind of compute the partial derivative of a vector transpose with respect to whatever the parameter involved, so it will just output will be the transpose of the vector. So that's what we have got here. Second is this partial derivative. Okay, so if you again, these are very simple things. You can like kind of explore at your room. So I'm not explaining them in detail. So what's the theorem tells? So partial derivative of x transpose ax with respect to x is a plus a transpose into x. Okay, so this is again another theorem of directional derivative. So by applying this theorem, you can represent this partial derivative, this component of the partial derivative by this, right? Now we simplify. So we got this formulation. This is something called the normal equation, right? In ordinary least square regression or any least square regression, this is called the normal equation. This is what we try to kind of find always. So if x is full rank, then we can compute the inverse of x. Another notion here: if x is full rank, x transpose x will also be full rank. Will also be full rank. Again, this is another theorem we are using from the linear algebra, right? So the actual theorem tells if rank of x is some k, then rank of x transpose x will be also same k. It's not only full rank, whatever the rank of k, x transpose x will have same rank, right? So if x is full rank, x transpose x will be also full rank, then we can take the inverse, then w can be represented as x transpose x inverse x transpose y. So this is called something called the closed form solution of the ordinary least square regression or just the linear regression, right? So when you say closed form solution, what the like kind of broad concept about closed form solution, we can compute like this is kind of not probabilistic, right? So this is like deterministic solution. So if it is deterministic solution, every time it should give us correct answer, right? So when it will give us correct answer always, because we are trying to minimize the loss function, it will always give us correct answer if the loss function is convex, right? So if loss function is convex, the minimum point will be, or local minimum will be global minimum, then we'll always get the correct answer. So let's try to see if the sum squared error, whatever the loss function we have used, that is convex or not. Again, for this, I'll use some concept of convex optimization. If you don't know, just skip it. Just understand this happens. If you take some convex optimization course from CS department, you will definitely understand these concepts. So the theorem tells the Hessian of convex function is positive semi-indefinite. If the Hessian of a convex of a function, not convex function, if Hessian of a function is positive semi-indefinite, then the function is convex, right? So what is Hessian? So Hessian is the second derivative. The Jacobian is the first derivative. So Hessian is the second derivative. So we have already computed the first derivative. The Jacobian we have already computed with respect to W. Now let's compute the Hessian. So if you compute the Hessian, again, taking second time derivative with respect to W of the whatever the Jacobian value we got, right? Now, whatever in the end, the simplification will give us 2x transpose x. So x transpose x, again, similarly, the way you saw here, this is the square of 2 norm was represented by x transpose x, kind of this vector transpose vector. So as it is a square term, it will always be greater than or equal to 0, right? If it is Hessian is greater than or equal to 0, what does it says? It's always positive semi-definite. Why it is why if Hessian is greater than or equal to 0, why it is positive semi-definite? You have to go to like kind of the uh, uh, concept of positive semi-definite of a particular symmetric matrix. So if X A is a symmetric matrix, X transpose X greater than or equal to 0. If this happens, then A is positive semi-definite. Again, these things you might have studied or must have studied actually as part of a linear algebra. I'm not discussing them. So that's what it says. If Hessian is so if this Hessian is greater than or equal to 0, then it will be positive semi-definite. As Hessian is positive semi-definite, loss function is convex. Right. So whatever the critical point we'll find while optimizing this loss function, that will be both local and global minimum. Right. So that's why this solution can be called as a closed form solution. Always it will hold. Right. Now come to one very basic scenario. So we started with y equal to some w into x, right? So if we go back to our kind of compact representation, we when we discuss about the compact representation, y equal to double transpose x or whatever by matching the dimensionality, we can write. So wx will match the dimensionality for multidimensional case, right? So you could have asked like, okay, my goal is to find w, right? Can't I just find w in a way that w equal to whatever uh, x inverse y somehow, right? So is not this possible? So something similar we're doing here only. So we're not taking the inverse of x. We're kind of converting x into some other form, x transpose x inverse and x transpose. So we have for the scenario also, if x is full, we could have taken x inverse y as the solution, right? Instead of computing this scenario. But this kind of scenario is very rare. Like this kind of scenario very rarely happens in real world data set. X being full rank, right? So when x will be full rank, so let's come to that. So this particular term, whatever we computed, x transpose x inverse x transpose, this is something called a pseudo inverse of x, right? So these are the terminology that is given by like kind of mathematicians. So there is no particular reason behind it. So it's not the exact inverse. They call it a pseudo inverse, right? So our scenario, our discussion was when we can compute W like this instead of computing X transpose X then inverse. That's again matrix multiplications are expensive, right? So that can be a correct solution if number of data points is equal to number of input dimensions. And this scenario very rarely happens in real world case. So in that case, we can directly compute W equal to X transpose X inverse Y, and that will give us the whatever the solution we want to find for this minimization. Right. So this is R min, not mean. Okay. But like in like 99% of the scenario, we will see this kind of case. Number of data points are more than number of input dimensions, right? So in that case, we cannot directly compute this because X inverse will not exist, right? So that's why we rely on this pseudo inverse to find this optimal W and B. Okay, now come to let me stop here. Any doubt on this? The calculus methodology, how do we compute the W value? Either in one-dimensional case or the multivariate case. Any doubt? Okay, so if there are no doubt, let me go ahead. So we discussed using calculus. Let's discuss using linear algebra. How do we compute the same thing? We want to find the optimal W only, right? So this requires little bit of linear algebra concepts. So again, so whatever required, I have put it here. But if you don't know, feel free to stop me because this is important for you to understand. Other things you can just search and find, but this is not very intuitive, right? So what is our input data? Input data is some x n cross p. Actually, this is p plus 1 because we have like augmented or one vector for the b parameter. Now the w is p plus 1 cross 1, right? Then y will be n cross 1. What's the major problem? We know n is most of the time n is greater than a lot greater than p, right? In that case, we cannot find the solutions directly. What do we do there? So if x, so for now, for brevity, I will just ignore this one. I will just say this is n cross p, right? So if this is n cross p matrix and we know p is less, then the maximum rank will always be p, right? So the maximum possible rank. I am not saying this is the rank. That's the maximum possible rank, right? But what is this computation? What is this computation happening here? This is, so whatever the y vector will get, this is just the linear combination of all columns of this x, right? So this is what we know from the matrix algebra. If you multiply um, some x into some vector v, so whatever the output you are getting, so this output will always be the linear combination of the columns of the first matrix. Let's say if you are doing v into x, the output will be linear combination of rows of the second matrix. Right? This is what we know from matrix algebra. Right? So y is always the linear combination of columns of x, and column space, we know column space is so the space in which each column vector is lying. Right? Column space is r to the power n. And what is the dimension of the column space? What is the dimension of the column space is the maximum rank of each column vector. And we discussed like maximum rank can be p here, right? Again, I have written p. It should be p plus 1 to be very exact. Dimension of column space is less than equal to p. So that if that is the scenario, we know y is lying in r to the power n, right? Y is lying in r to the power n, but this multiplication we are saying it is lying in p dimension because this is p dimension. After this multiplication, the maximum dimension will be p only, right? So the rank is p, meaning p dimension, right? So what will happen then? So if you try to kind of visualize this, so let's say you know the how to compute this solution for x equal to b, right? X equal to b. You create an augmented matrix here of a b and kind of try to eliminate or simplify this. So here, because p is less than n, you will find some rows here they're completely zero. right? But B, whatever the B here, we have B here is in our case, not to confuse with our the bias B. Here our B is Y values. So here we don't have non-zero, sorry, we don't have zero B values. We have non-zero B values here, right? Then this will give us kind of no solution scenario, right? So how do we get rid of this? We project this Y onto XW. XW we know is lying in p-dimensional space, right? So if we project Y into this XW, then now this issue has been resolved, right? These components will become zero, right? So if we project, there will be some error. So that error component is called E here. E is Y minus XW, right? So what we are projecting onto Y, we are projecting onto the column space of X, right? And this error is normal to the this column space always, right? This error vector. So we'll use this concept. So this error vector being normal to the column space, whatever the column space. So now if we apply that concept, every vector in the input feature matrix, if you do the dot product with that whatever the error E vector will give us zero, right? So in turn, we can write X transpose E equal to zero, and E we can replace by X transpose Y minus XW. This is the error component, right? Now, if you kind of open this bracket, this is X transpose XW equal to X transpose Y, and W will be whatever the closed form solution we saw earlier using calculus, the same closed form solution. Exactly. Right. So generally, like if you don't know, like if you don't want to apply this whatever this calculus method, you can directly do it using linear algebra. But if you do this using linear algebra, you cannot say with guarantee that this whatever the closed form solution will be the correct solution every time. So for that, you need to definitely understand and know the calculus methodology, right? Because you have to compute Hessian there. So before going to Hessian, we have to compute Jacobian. So once you are computing Jacobian, you already know the closed form solution, right? So this is the theorem I discussed earlier. If X has rank P, then X transpose X will have also rank P. Okay. So these closed form solutions. So we saw closed form solution, but so are we satisfied with that? The answer is no. Why we are not satisfied with that? So any doubt again for the linear algebra solution? Any doubt for the linear algebra based analysis? How do we find this W? Okay. Yeah. So what are the major concerns of this closed form solution? First and the most important concern is this computation of X transpose X inverse, right? So this is very much computationally expensive if P is very high. Even if P is not high, like if P is also 1000 so X is 1000 dimensional vector, 1000 to the power 3 will be very high also. So the computational cost of this closed form solution is very high. Generally, we can approach linear regression using closed form solution if X is very low dimensional data. Also, another major problem is numerical instability. So we discussed multi-collinearity, right? So this is no multi-collinearity was assumption for linear regression. So what's the problem happens when the input features are multi-collinear? So if the input features are multi-collinear, the thing is we're relying on this rank, right? So rank will be low. If rank will be low, all this computation will be unstable. So whatever this X transpose X inverse, this computation will not be very much accurate if rank becomes very low, right? So if we have a lot of multi-collinear features, then linear regression is something we don't apply. So I'll not. So for now, I'm saying we don't apply, but we apply with some modification. We'll discuss that later, right? This ordinary least square regression we cannot apply if there are a lot of collinear features. So that is called multi-collinearity. So that's also another disadvantage of whatever the least square solution. Another thing is if X, so if X, the input features are very high dimensional and there are a lot of data points, the memory requirement will be also very high. So these are very basic concerns. There are much more important concerns, like not very important, but let's say you can say about nonlinear relation between x and y outlier points. There are also concerns, but there are approaches how do we address them. But this is something we cannot easily address using the closed form solution, and this is something we cannot easily address. So this is one, two, three. Right. So multicollinearity, there are approaches how do we address this. We'll discuss. Okay. So to majorly tackle this first point and the third point, we rely on the gradient descent. So instead of computing this closed form solution, computing the W through this closed form solution, we can compute something called gradient descent. Like we can perform the gradient descent given the input data points to get the exact same solution W. Right. So gradient descent, as we know, is kind of iterative algorithm. Again, I'm just confirming gradient descent was covered by Sir, right, while covering neural networks. Okay. So I'm not discussing the nitty-gritty. So you have to go in the negative direction, opposite direction of the gradient, and what all these gradients, all these things you know, right? So again, so we'll use those concepts. So our initial, so this is our W, right? So if, but we don't know, this is the W we found using closed form solution, right? So this is the parameter we kind of would try to achieve using gradient descent also, right? So what was our sum squared error? Sum squared error was y minus x w square of the second norm. And if you kind of try to take the derivative, so what is our gradient descent iterative step? Every step t plus one, you take the t w and with some learning rate subtract this derivative of the last function, right? At that w value. Right. So that's what we have to do. So for that, we have to compute this delta L. Delta L we have already computed during Jacobian process, but I am just rewriting here. Um, yeah. So now what it is giving us, like you can start with any random W, and that will be p plus one dimensional vector because we have the bias term also. Now we have to compute this first term, that is x transpose y, that's p-dimensional vector. Then another x transpose x, that is some should not be k, should be p plus one, p plus one. Yeah. Again, p plus sorry, p cross p matrix. So because x transpose will be p cross n and x will be n cross p, right? So you iteratively compute this thing. So when do you stop? You stop when you have this loss is like kind of you have a threshold and this loss has gone down that threshold, right? So if you do this iterative step, you will converge to this W value only, right? So we don't get this W value explicitly using gradient descent, but we follow this iterative approach and we'll get this W value. But this iterative approach can also be slow if we have like kind of a large number of n and very high dimensional data. So generally, dimensionality doesn't affect the time complexity of the gradient descent. I'm talking about the time complexity to run the gradient descent, but dimensionality might affect how fast. Let's say this is a loss curve. So dimensionality might affect how fast you are converging to the minimum point, but it doesn't affect the time complexity for each iteration, right? So how fast it is converging, it depends on like what algorithm you are using, what's the like kind of the relation between each features among each features in the input data also. So for that, if time permits, again we'll discuss the variations of gradient descent. So considering different or like kind of different possible relationships among input feature vectors, there are different variations of gradient descent. So if we are unable to cover as part of your syllabus, you feel free to check the things, check those variations. One is stochastic gradient descent, then is minimized gradient descent, There are like kind of advanced variations like Nestro acceleration computation, then Adam. Sorry, in between there are two things: Adagrad and Adagrad RMS Pro. Okay, so these are very like currently we have like this is the best possible algorithm for this gradient computation till date with some modification, but we rarely use NAV or Adagrad or RMS Pro. We either use minimized stochastic or Adam in a kind of any machine learning algorithm in recent days, right? So if we have like kind of let's say we're working with textual data, Adam works very easily. If we are working with tabular data, then the stochastic or minimized gradient descent works very sophisticatedly, or kind of the convergence is very fast, right? So the nuances behind this you can explore. If time permits, we'll definitely cover as part of this course, right? So one important thing we got rid of in during gradient descent iteration step is computation of this inverse, right? So this inverse was taking us like order of pq, right? Cubic time complexity. That is now we have got rid of, right? So that's how it is helping us to save the time complexity, right? So this is all about how do we get this the W value, the parameter of this linear regression model. Now we'll see different variations. Like if linear regression, the relationship between input output is not linear. If the relationship among the features are not co-linear. If they are co-linear, what happens, right? So how do we tackle those scenarios? So first thing is how do we tackle the case of outliers, right? So in case of linear regression, how do we tackle the case of outliers? So we saw how the approach for tackling outliers in SVM. So by incorporating Lagrangian. So some things exactly similar we'll do here. So before that, let's understand what happens to the linear regression solution, the ordinary least square regression solution, if we don't like employ any fancy mathematics, right? So let's say these are four outlier points, and we know these blue points are like kind of nicely plotted, and they are the correct data points, and these four are the outliers. If we are devising some algorithm, we should be able to kind of ignore these 4 points and draw the best fit line using the blue points, right? So if you draw the best fit line using the blue points, you will get this orange line. But if you employ ordinary least square solution without kind of removing this outlier points, you will get this green line, right? All these quotes and all again I will share with you. But last during SBM also, few people asked me about the code that I showed. I didn't share intentionally because you have to do your lab. So again, this also I will share after your lab for linear regression and logistic regression is done. Okay. Yeah. Now coming to the point. So what happens because of this very large outliers towards this side, like kind of bottom side of this figure, the kind of the hyperplane got shifted right towards these large outliers. So why it got shifted? Because somehow this x, because they are very high value, they are like kind of able to get very large W for this X. If you get very large W for this particular outlier points, then this whatever the this is W, right? So the normal to this W or W vector we know we discussed during SVM also. So this will get shifted towards those data points which attracts a high W value. So that's what we do as part of Lagrangian when we did SVM also, controlling the growth of W. Right? Exactly same thing we'll do here. Yeah, so linear regression was our the last function was y minus x w square of second now. In in order to tackle these outlier points, we'll incorporate something called Ridge regression, where we are adding this L2 normalization. This is called L2 normalization. Right. So what is L2 normalization? It's what we are trying to do. We are trying to control the growth of W. How we are trying to control the growth of W, because this is the overall term you have to minimize. This LW you have to minimize. If this will be very high, then overall computation will be high. Because our objective is to minimize this, you have to minimize this also, the norm of W also, right? So this lambda is a hyperparameter again. So this you can experiment during your lab and see how it affects, right? Right. The main goal is because we are trying to minimize this L. So by putting this extra term, we're trying to control the growth of W. So that's how it is helping us to kind of not get rid of outliers, neither SBM nor linear regression, this solution of the linear regression, they don't get rid of outliers. The outliers are there, but they control the growth of W so that the value W for these outliers will be insignificant, right? So there are approaches how we'll get rid of X completely and only consider these blue points and draw the best fit line. But this ridge regression or any modification to linear regression, they don't do that explicitly, right? So again, now we have to see. Under ridge regression, now what will be the optimal W? So we saw without ridge regression using linear regression, we know this is the closed form solution. We know like X transpose X inverse X transpose Y, right? And using gradient descent, we saw how do we do it. Now, when we apply this ridge regression, what will be the change that will be applied to W? We'll see how a W will be modified, right? How L is modified? L is modified by this term only, right? Now again, you expand the way we did, same approach. Once you open this multiplication, then you take partial derivative with W. Then once partial, so we don't need B. So B is now part of this W, sorry. So again, you apply the kind of the theorems we discussed. So if you do that, so what the W value will get, all the steps are there. You can just follow them. It's not very hard to follow. So what's the W value will get? X transpose X plus lambda I. So some extra term lambda I you are getting here. What is this lambda I? We'll see now. Right? So lambda is the hyperparameter we know. Why this lambda I was required at all to kind of tackle these outlier points or some other scenarios, right? So again, so this is the closed form solution for ridge regression. Closed form for ridge regression. Now, if you are saying this is closed form, we have to prove also, okay, this loss function is convex. We proved this loss function is convex. Now we have to prove this loss function is convex, right? So again, you follow the same approach. You find the Hessian. If Hessian is greater than or equal to 0, then it is, we know PSD. But beautifully, this Hessian is strictly greater than 0. So this is a positive definite matrix. So whatever the loss function we are getting, so this is positive definite, right? So earlier we got positive semi-definite. This is positive definite. So this is something called strictly convex. Strictly convex. So what's the difference between strictly convex and convex? All these things again, I'm leaving for the time being, so you can check them out. So our major target is getting convex functions. Strictly convex is not our goal, but during like formulation we got the strictly convex. That gives us some nice property, but it's not necessary for us, right? So again, why this is greater than equal to 0, that's the important thing we have to see. So this part we know this is positive, right? This kind of 2 norm of X, right? So that's always positive. And this is lambda into I. So this lambda into I, so what we are saying here, uh, if you would do this again, as I discussed, the quadratic form you have to apply. So X transpose AX, right? If you apply the quadratic form and see if this quadratic form is greater than 0 or greater than equal to 0 or less than 0, From this, you get to know whether it is PD, PSD, or ND or NSD. ND, NSD are negative definite or negative semi-definite, right? So once you apply this quadratic form, the quadratic form here is a W transpose X transpose X plus lambda I into W. You kind of open this multiplication. So what's the output of this quadratic form? X trans X W second num square and lambda W second num square. So again, both are like kind of norm square, so they will be always positive. Uh, as they both are always positive, I mean this the claim that this Hessian is also positive is true, right? So our point now was how this is helping us, right? We got okay, this is nice convex function. This is closed form solution. How this particular thing is helping us to get rid of our outlier. So what it can do, right? So this W for the outlier points, this I is like kind of identity matrix, right? Right. Again, so there is some nuance I missed here in the slide. The nuance I am talking about is uh, okay. So in this closed form solution, when we are saying W is B and W, right? So the complete vector is B is there and W is also there. W0 to WP, everything is there, right? Right. Generally, we don't. Not generally. Actually, when you solve this, when you open all these things, this I, this is I is not exactly I. This is 0 for B and 1 for all other things, right? Right. So if you see your optimization packages are for PyTorch or NumPy or sklearn anything, so they do some extra matrix multiplication here to force that corresponding to B, the value of this particular multiplication will be 0, right? So that I think for implementation side you should know, maybe you need for part of your lab. Okay. Uh, Now we'll see how we're able to kind of get rid of this the effect of outlier. So if like kind of some data points are outlier, some X are outlier. So even if this like this is identity matrix, this lambda value can be adjusted in a way that this W will have very low effect on this X values, right? If lambda is very small, this overall multiplication will be also very small. So why it will be small? Sorry, I said opposite. If lambda has to be very high here, if you have a lot of outliers, so lambda has to be very high. If lambda is very high, the overall value will be very small. Why it will be? Because you are adding this some scalar term to this X transpose X, taking inverse. The inverse will again be small if lambda is very high. So you have to see part as part of your lab, like changing lambda to low value and high value, and how it helps to get rid of these outlier points. Okay. So overall, least square regression has some broader concerns. One is again we're assuming they are capturing the linear relation, only linear relation. What about if we have this kind of non-linear relation between x and y? This is a sine curve, right? So this should be our actual prediction, but we are predicting this. So how do we do this? So again, we learned kernel trick in SPM, right? So I'm not explicitly telling you how do we apply kernel trick, and this will be your lab question. Okay, so you can prepare for this. One of your lab question will be how do we apply kernel trick to the linear regression. So there will be two questions. One of first question will be this, right? So again, the problem is a problem with kernel trick. I'll discuss that only. So issue with kernel trick. So here you have to you need to know you need to know the nonlinear function beforehand. So if you don't know the what is the exact nonlinear relation between x and y, you cannot apply the kernel trick also. right? So it's not like I'll directly ask you the kernel trick in the lab. I'll be giving you some helper theory. You have to read that and write the code based on that, right? So that theory I'm completely skipping. That will be part of the lab. And now how do I apply kernel trick? So there you will realize why we need to know this nonlinear function beforehand. Without knowing this beforehand, we cannot apply, right? And it is very sensitive to large outliers. And again, the interpretability part is not there, right? Code walkthrough again we'll do tomorrow. We have consumed the time. So tomorrow we'll discuss the logistic regression and code walkthrough for both linear and logistic regression.